Welcome. I'm Ed Gernert, co-founder of Frontier Design Automation. This talk is about a practical problem every EDA tool team faces. How do you keep up with the flood of regression results that come in every time an engineer commits code? And how do you stop that triage work from eating your best engineer's time? We built something called HAL using Hermes to solve this. Today, I'll walk through the architecture and what it's done for our team's velocity. Quick background on who we are. Frontier is a small, focused team, 8 employees, building the next generation of IC routing technology. Every hour we spent on code triage is an hour not spent on the actual routing problem. John Cooper and I founded the company in 2019. Both John and I have built 2 prior generations of shape-based routers commercially. This is the third. The reason our situation is relevant to the HAL story: we cannot afford our best people spending hours triaging regressions after every commit. That constraint drove us to build HAL.
Let's start with the problem space. On the complexity side, modern SoCs exceed 100 billion transistors. The number of manufacturing constraints at N3 and below has grown exponentially. A router built for 28 nanometers doesn't just need to be faster at 3 nanometers, it needs to reason about a fundamentally different constraint set. Delayed tapeout at advanced nodes costs millions of dollars per week. On the tool side, all commercial routers were architected in the early 2000s. The multi-core revolution largely passed them by. They require extensive manual tuning from physical design engineers to close a design. This is the market Frontier targets, not just faster or higher capacity routing, but a shape-based router built from scratch for the constraint environment that exists today.
CI, continuous integration, is the practice of running your test suite on every code change. Commit, machine runs tests, you get results. For us, an engineer commits a change to the routing engine. Kaleido, our shape-based autorouter, runs against our full set of regression designs, 150 plus real circuit designs, and we get back a structured report: route quality metrics, DRC violations, runtime, completion rate per design, and more. That last step, triage, is where the problem lives. Someone must read those results. Which regressions are real bugs? Which are noise? On a team moving fast, that question comes up multiple times a day. HAL replaces that human intervention. Not just by flagging, HAL can classify, diagnosing where it can, and either proposing a fix or opening a pre-populated bug ticket. Before going deeper into HAL, a quick word on what we're building. Kaleido is our shape-based IC router. At advanced nodes, the interaction between adjacent wires is too complex for any grid map tool. Within Frontier, we have 4 major architectural differentiators. AI optimization. All routing decisions within the tool uses AI-driven heuristics, not just the CI pipeline. Massive parallelism, genuinely multi-threaded. Modern servers have 64 to 128 cores. We use all available threads. Modern architecture, modern containers, no 1990s scaffolding in the critical path. New AI algorithms, no artificial separation into global, track, and detail routing phases. AI handles routing as a unified problem, all without human intervention. Triage. This is one of the specific problems HAL was initially built to solve. Every time an engineer commits, multiple times a day on an active team, a regression run kicks off. The run takes time, comes back with results, and someone has to look at them. If you fall a day or a week behind on triage, finding the root cause of a regression requires digging through a lot of history. HAL solves this by making triage happen automatically, within minutes of the run completing. So what does HAL actually do after every commit and automated regression run? First, it classifies each failure. 3 categories: a regression, something passing and now isn't; a known flake, a design that fails intermittently; or a new defect, something we haven't seen. Getting that classification right is the core of the triage problem. Second, for anything it can diagnose with confidence, it proposes a fix. Not a vague suggestion, an actual code diff, with a rationale explaining why it believes this is the cause. Third, for anything it can't resolve, it opens a bug ticket. It creates a pre-populated ticket, the classification, the relevant git diff, the specific designs affected, and HAL's best hypothesis. When an engineer opens that ticket, the groundwork is already done. End result: within minutes, an engineer knows his changes are valid or sees a proposed fix waiting for review, or a pre-filled bug ticket in their queue. Nobody sat down and read regression logs. HAL contains four basic layers. Foundation, Kaleido, our GUI-driven or command line router. It runs against OA-based circuit designs and produces structured output, per design metrics, DRC counts, runtime, completion rate, and more. That structure is critical. HAL never parses log files. It gets clean, machine-readable data. Comparison layer diffs the current run against the historical baseline. It determines what changed. Classification happens here. Context retrieval. HAL assembles focused context, the changes in the commit, the specific designs that regressed, the relevant source code slices based on blame and call graph analysis. Confidence gate, the key architectural decision. Whether HAL's proposal goes to a proposed fix is gated on a confidence score. Below the threshold, bug ticket. Above it, proposed fix with actual source code. I'll address the question I know is coming. Does design data leave your network? No, and it's architectural, not a policy statement. Frontier runs both HAL and our developer tooling against ALLM using an enterprise license. Our data is contractual protected, and Anthropic does not train on or use any inputs or outputs, period. This protection is enforced at the org level. What flows through HAL is Frontier's own routing source code snippets and regression metrics, not the layout designs. Customer data, OA databases, net lists, and layout geometry are not part of HAL's data flow. This was a deliberate design decision. We knew semiconductor customers would ask this question, and we wanted the answer to be architectural, not contractual. 3 reasons why this is the right moment and why it wouldn't have worked a year ago. First, the LLM models are actually good enough now. 12 months ago, asking an LLM to reason about production C++ routing code and produce a credible diagnosis was at the edge of capability. Today, it works reliably enough to justify the infrastructure investment. Second, our structured output gives HAL a real advantage. A lot of teams trying AI and CI struggle because what they're classifying is messy, raw log output, stack traces, intermittent failures. We have clean, structured, per design metrics because we designed Kaleido to produce them. That structure is the foundation everything else builds on. Third, the alternative doesn't scale. We're growing. More engineers, more commits, larger regression suites, and more constraints. Building HAL now, while the team is small and we can iterate fast, is the right call. For CI, here's where we are. Foundation is in production. Kaleido, regression infrastructure, structured result format, baseline comparison. The classification layer and context retrieval pipeline are complete and running. Autonomous proposed fix creation is active. Engineers are already seeing HAL triage appearing in their bug queue. First pass bug classification, which was entirely manual, is now automated. When HAL can't resolve something, it opens a ticket. The bug arrives pre-populated. Classification, relevant diff, affected designs, hypothesis. An engineer opening that ticket is doing verification work, not detective work. Let me show the complete picture of how our engineers actually work. The IDE we use is Visual Studio 2026. Inside Visual Studio, we use a Claude extension connected to our secure LLM. Claude has access to the full codebase. It can reason across the whole project, not just the file you have open. The workflow: HAL surfaces a regression, pre-populates a bug ticket with everything it knows. Engineer picks up the ticket, opens the relevant code, asks Claude to help diagnose. Claude reads the commit diff, looks at the specific designs that regressed, reasons about what changed in the routing engine, proposes a fix with rationale. Engineer reviews, refines if needed, commits. HAL validates the fix on the next regression run. Engineers spend this reclaimed time on the actual hard problems: algorithm design, constraint handling, performance tuning, not reading log files. I want to be clear about what we're claiming and what we're not. We are not claiming AI has solved IC routing. Routing involves exponential constraint spaces, multidimensional quality trade-offs, and physical properties that don't yield easily to pattern matching. We expect routing to stay hard for a long time. What we're claiming is that CI triage is a different kind of problem. Triage is read structured data, compare to baseline, classify the difference, assemble context, propose an action, or escalate. Pattern matching and structured comparison. Exactly what LLMs are good at. We're not trying to overall automate the hard problems. We're trying to get the time-consuming but tractable problems out of the way, so engineers spend all their time on actual routing algorithms. That's the thesis. HAL is reactive. Something breaks, it automatically responds. HAL's current roadmap also extends this to proactive, goal-directed work. Using directed mode, the user sets a goal for HAL. Performance optimization. An engineer gives HAL a specific goal. Improve runtime on this design class by 15% without degrading route quality. Find the bottlenecks and propose a fix, all without changing routing results. HAL automatically proposes changes, runs regression, reads the metrics, decides whether it moved the needle in the right direction, and iterates until the objective is met. Test onboarding. Adding new designs to the regression suite is time-consuming work. Claude skills will automate the scaffolding, ingest the design, establish a baseline, wire it into CI. What currently takes an engineer an afternoon becomes a single action. Design generation. Identify gaps in design space test coverage or new tech nodes with only a handful of designs. HAL will generate synthetic designs to fill those gaps. Smart scheduling. A classifier trained on which files changed and historical regression data estimates whether a given PR is likely to move the needle. Low-risk PRs batch into a single daily run. High-risk PRs get the full suite immediately. A natural efficiency optimization as the benchmark set and team scale. Documentation drift detection. At 200,000 lines of C++, documentation is almost certainly drifting from the code. Claude can regularly compare both, flag divergences, and propose updates as reviewable PRs. Directed mode is fundamentally different from CI triage. It's not detecting and fixing breakage, it's pursuing an engineering objective autonomously. The same confidence gate and right path restrictions apply, but the loop runs until the goal is met. The common thread in directed mode. A human sets the objective and approves the result. HAL handles the measurement, iteration, and proposal work in between. To summarize the complete picture, the routing engine uses AI-driven decision-making throughout, not as a wrapper around a legacy tool, but as a native part of how every routing decision gets made. No manual setup or tuning between phases. The AI is inside the routing loop, not layered on top of it. HAL automates the full CI triage loop. Regressions get classified, diagnosed where possible, and surfaced as either a proposed source code fix or a pre-populated ticket, without human intervention. Engineers work in Visual Studio alongside Claude with algorithms, code reasoning, as well as setting goals. HAL understanding a 200,000-line C++ codebase conversationally, proposing changes and reviewing diffs. The cost question is on everyone's mind. We run regressions on-prem, so the marginal cost per regression run is compute time, hardware we already own. Claude developer tooling, roughly $100 per day. Full code-based reasoning, conversational code editing, diff review. For our team of engineers, total AI tooling cost is roughly $3,000 a month. Against the cost of the engineering time, it's reclaiming. The return is measured in days, not months. One meta point before we close. Over 90% of this presentation was created automatically by HAL. The slides, graphics, and speaker notes were all generated from a Python script that HAL wrote. I provided the engineering facts, the architecture decisions, the failure modes, the real metrics. HAL structured it, built the script, and produced this presentation. The video and audio version was created by HeyGen AI using a single photo of me and a few lines of voice script. That's not a parlor trick, it's the point. The tools we've been describing built this talk. What you're looking at is the productivity leverage we're claiming. This presentation from start to end took less than a day to create. Thank you, and thanks to the SI2 team for the opportunity to present. If you're working on physical design tooling, AI belongs in your CI pipeline. If you have any questions, we will be happy to answer them. Thank you.